Kinetic separations of mixtures using zeolites or metal organic frameworks are of great industrial interest. My objective today is to analyze kinetic separations using matrix algebra and matrix calculus. For background on kinetic separations, I refer you to my paper in ACS Omega 2019. For background on matrix algebra and calculus, consult the textbook Multi-Component Mass Transfer that I co-authored, and this was published in 1993. Further background on kinetic separations is available on my YouTube video titled What Drives Kinetic Separations? An important characteristic of kinetic separations is that for binary mixture uptake within crystals of zeolites and morphs, the transient uptake of the more mobile component experiences a pronounced overshoot. As an example, I show here experimental data for uptake of nitrogen and methane in LTA4A zeolite at a temperature of 194 Kelvin. The bulk gas phase contains 50 kilopascal each approximately of either component. We note that the component loading of nitrogen experiences a pronounced overshoot and equilibrates to a lower loading with the progression of time. Methane experiences a monotonic approach to equilibrium without any undershoot or overshoot. Here's another example of uptake of CO2 and ethane in DDR zeolite that consists of cages separated by 8-ring windows. Experimental data were obtained at a temperature of 298 Kelvin, and the partial pressures of both components in the bulk gas mixture is 20 kilopascals. The more mobile CO2 experiences an overshoot in its loading, and as time progresses, the component loading decreases to its equilibrium loading. The ethane equilibrates in a monotonous manner. Here's experimental data for the same mixture, CO2 ethane and DDR zeolite, but with different partial pressures. The partial pressure of CO2 is 40 kilopascal, and the partial pressure of ethane is 20 kilopascal. Again, we see a pronounced overshoot in the loading of CO2 during the initial stages of the transient uptake. The modeling of the transient uptake requires the solution of the partial differential equation describing the spatio-temporal development of the molar loadings Q sub I for each of the components. The partial derivative of the molar loading with respect to time is related to the interfacial fluxes of the component, and the flux of each component is related to the chemical potential gradient of that component. D sub I is the Maxwell-Stefan diffusivity. The modeling details are available in my 2019 publication. The component gradients of the chemical potentials are relatable to the gradients of the molar loadings via a square matrix of thermodynamic correction factors. The off-diagonal elements of this gamma matrix has significant off-diagonal elements. Indeed, the transient overshoots are ascribable to the non-zero off-diagonal elements of the elements of thermodynamic correction factors. So the transient overshoots are engendered by thermodynamic coupling. The details of this derivation of these equations and drawing this conclusion is available in my publication. See also my YouTube video, What Drives Kinetic Separations. The second important characteristic of kinetic separations is that if the component loadings for transient uptake within a single particle are plotted in composition space, the equilibration trajectory follows a serpentine path. This is the serpentine path followed for equilibration of 50-50 mixtures of nitrogen and methane in LTA4A zeolite at a temperature of 194 degree Kelvin. The continuous solid line is the solution to the Maxwell-Stefan equations shown in the foregoing slide. For uptake of CO2 ethane mixtures in DDR zeolite, the component loadings when plotted in composition space also show a serpentine trajectory, and this trajectory is described quantitatively by the Maxwell-Stefan model shown here by the continuous solid line. The same is true for CO2 ethane uptake in DDR zeolite when the partial pressures of CO2 and ethane are 40 kilopascal for CO2 and 20 kilopascal for ethane. We see that the approach to equilibrium is not monotonous but proceeds in a serpentine manner. We now examine the mathematics that dictates the serpentine equilibration trajectory in composition space. In proceeding further, it is convenient to reformulate the Maxwell-Stefan equations by shoehorning the set of equations into the form shown here, which is the generalized Fick's law, where we have defined a two-dimensional square matrix of Fick diffusivities. This matrix of Fick diffusivities is a product of two matrices, a diagonal matrix with elements D1 and D2, which are the Maxwell-Stefan diffusivities. This matrix is divided by the matrix of thermodynamic correction factors. For the specific system, nitrogen, methane diffusing into LTA4A zeolite, the experimental data shown in the foregoing slides are described by the Fick diffusivity matrix shown here, where I divide the Fick diffusivity matrix by the square of the radius of the crystallite. We note that the off-diagonal elements D1, 2 and D2, 1 have significant magnitudes in relation to the diagonal elements. The eigenvalues of this matrix can be determined, and the two eigenvalues are shown here. This is the larger eigenvalue. This is a smaller eigenvalue. Corresponding to each of these eigenvalues, we can determine the eigenvector. The first eigenvector is the fast eigenvector. The second eigenvector corresponding to the second eigenvalue is the slow eigenvector. Now I plot the component loadings in composition space. The y-axis is the nitrogen uptake, the x-axis represents the methane uptake, and this is the experimental data. The fast eigenvector is shown by the continuous solid straight line. The slow eigenvector is the solid blue line. During the initial transients, the trajectory followed during the transient equilibration process is dictated by the fast eigenvector. Towards the later stages of the equilibration process, the trajectory is dictated by the slow eigenvector. Indeed, these two straight lines provide guide rails within which the experimental component uptakes must reside, and this explains the serpentine character of the composition when plotted in composition space. The next step in our mathematical analysis is to transform the coupled differential equations described in the previous slides into a form such that the equations become uncoupled. In order to do this, the important step is to construct a matrix P called the modal matrix. This is a two-dimensional square matrix where the two columns are the eigenvector, first eigenvector, and the second eigenvector. This is the fast eigenvector, this is the slow eigenvector. An important characteristic of the modal matrix P is that if we take the efficient diffusivity matrix that has significant off-diagonal elements, if we pre-multiply by the inverse of the modal matrix P and post-multiply by P, we obtain a diagonal matrix with the diagonal elements equal to the eigenvalues. And if we pre-multiply the component loadings Q for components 1 and 2 by the inverse of the modal matrix, we obtain pseudo component loadings, which I denote by QQ. The pseudo component loadings need not have positive values. Indeed, in the example of nitrogen methane uptake in LTA4A zeolite, the pseudo component loading of methane is negative over the entire equilibration trajectory. The important result of such a transformation into pseudo component space is that the pseudo components equilibrate independent of partner species, and for uptake within a spherical crystallite of radius r sub c, the equilibration trajectory is described by this set of equations shown here, and each component equilibrates with its own eigenvalue. And just to remind ourselves, the two eigenvalues for nitrogen, methane, and LTA4A are shown here. I plot here the uptakes in terms of the pseudo-component loadings, the red circles are for nitrogen and the blue squares are for methane. For methane, I plot the negative of the pseudo-component loading because the pseudo-component loading itself is negative, and therefore it is convenient to plot minus QQ2 for methane rather than QQ2. We note that the equilibration trajectory followed by the pseudo-component loadings have a monotonous equilibration character, and the straight lines are the equilibration trajectories obtained by solution of this analytic equations with the two eigenvalues shown here. In pseudo-composition space, the pseudo-component loadings show a monotonous approach to equilibrium. This is the equilibrium value, this is the initial value.